Hi Frank, this is Dick Riley from Ophir Spirocon. I'm going to send over to you a report that we did for Corning. It's not proprietary information by any means, but it does demonstrate the concept of this approach of being able to profile, measure, and understand the intensity of large beams. The two businesses that Ophir Spirocon represents is power measurement and beam profiling. That's all we do. And profiling and measuring beams from micron sizes up to literally tens of inches is not uncommon for our capabilities to have to be challenged with. So if you take a look at this report that I sent over from Corning, it demonstrates where we were looking at a large beam to simulate a situation with Corning where they needed to understand the size, the shape, and the intensity of a particular source they were working with. If you look at the first page, what I did to simulate the situation was to use an LED flashlight and position this onto a piece of opal glass. This is larger than normal, larger than I normally use. It's available through Edmund Optics. It's an image plane we use, suitable for that wavelength, and we set up the flashlight to point directly at the image plane and be able to, and because it's white light, we can actually see that we're capturing 100% of the beam for this demonstration purposes. On the second page, you'll see where the light is now on and it's projected onto the image plane. Happens to be back about 12 inches or so, and we have flooded that whole area. Now, to be able to see this, if you go to number 3, you'll see that we set up the camera with a focusing lens on the opposite side of the image plane, and we're looking directly at the beam. Now, this particular camera is actually an older style camera. The current camera looks like this. This is with the focusing lens attached, so it's a relatively small camera, CCD, 4 micron pixels, 5x7 array, and we adjust the focusing lens so it's focused directly onto the image plane. If you go to the next page, which shows you a picture of the beam, this is actually what the camera sees when it looks at that white light as far as intensity and size and shape of that flashlight. What we've done is we've added the profile so we know what the profile is from an X and Y. That's, you see that on the left hand side and at the bottom. We can also understand the intensity. This beam actually has a weak spot in the center of the beam. From a graphic standpoint, if you go to the next page that shows the three-dimensional image, you'll actually, this just further emphasizes the fact that the beam does have an intensity weakness in the center of the beam and is not uniform in that regard. So it was a way of being able to demonstrate that we can see the intensities, we can see the size, we can see the shape. If you go to the last page, some of the things we measure, and we measure a variety of things if necessary, but in this case we are measuring just the size. In this case it was a D4 Sigma. It was a 55 millimeter beam, so we're a little over 2 inches in diameter. They wanted to measure the flatness and the uniformity. We can also measure the intensity and the uniformity of the intensity. So there's a variety of things that we can measure, more than what is ever really needed. But using this kind of camera, which is a nice little compact device, it's a USB 3 camera. Software comes with it. The lens is separate, relatively inexpensive, and not at all as expensive as if you went through a lens manufacturer. And with the image plane, as I said, runs less than $100 from Edmund Optics. That this kind of beam imaging, beam profiling, and beam measurement is a very simple process. So any questions, let me know, and it's easy enough demonstrated. I could stop by and we could set it up and actually show you how it works. So talk to you soon. Have a good weekend. Bye.